I invited Sam to come on to my podcast, and we started talking about his paper. So the podcast is going to really be about the paper that he co-authored with David. But he started to explain at a more basic level how quantum physics works. And so we said, you know, we should record this. We should put this up on the YouTube channel. And then Sam had the idea, hey, let's invite people. And that way we can get other people's questions and things like that. And this is really a cool presentation. He gives you the very basics of exactly what quantum physics is. And it's one of the best explanations of it that I've seen that's mathematical. I mean, avoids the kind of the layman's approach to it. You never quite get it if you try to explain it through English or through a natural language. So we thought this was very cool. And that was why we decided to go ahead and do this. So Sam, go ahead and take it away.
Cool. Yeah, so thanks so much for having me. As Bruce said, this presentation came about through a conversation that we had about my and David Deutsch's paper. And what I wanted to do is I wanted to give like an introduction to quantum theory to those people who are not very familiar with it, but who know perhaps just some mathematics, some basic mathematics and some basic physics. And what my presentation is really about is this idea of what we call a Q-number descriptor. And presumably that term will not mean much at the moment. And the whole aim of my talk is to give you an idea of what a Q-number descriptor is and what role it plays in quantum theory. And as I will argue, I think like most, if not all of the structure of quantum theory is contained in this idea that the descriptors of physical systems are Q numbers, and I'll unpack that statement throughout the talk. And where I want to begin is with this idea of a descriptor, which is not a widely used term. And I think it's kind of specific to the subculture of physics that I and others are in. But especially to those people who are not very familiar with quantum physics, it will be, I think, a new term. So to give you a sense of what I mean with a descriptor, I thought it would be nice to just consider a very simple classical system. And perhaps the simplest classical system, at least that I could think of, is just a particle on a line. And a particle on a line has a position which is just some point on the line. And that position is indicated by a number x. And this number, because it's a point on the line, it is an element of the real number set. And it is the descriptor of the one-dimensional particle that I'm thinking of, because all the different possible states of this kind of is kind of a timeless one-dimensional particle. It's completely stationary, but all the different physical states that it could be in are denoted by this variable x, which is an element of the real numbers. So a descriptor, and the way that I will be using it during the talk, means a kind of variable whose different values map onto all the different physical states of a system. And in classical mechanics is completely defined by what we call C-number descriptors. So classical mechanics is described by C numbers. So consists of C numbers. So by this, I mean that whenever you have some physical system, the possible physical states of that system are always described by C numbers. And so I have just had the example of the one-dimensional particle with a position. You can also think about, say, a pendulum with a kind of angular displacement. Well, that angular displacement will be some number between 0 and 2 pi. And it's again a C number, because any number between 1 and 2 pi is an element of the real number line. And likewise, any other descriptor is always a C number. Sometimes they're vectors consisting of C number components. Sometimes you can even use matrices, but the essence is always that the thing that describes what the particle is doing or what the physical system is doing is a C number. And one of the consequences of this is that the thing that you end up measuring is the particular C number. So if you were to measure the position of the real number, or sorry, of the one-dimensional particle here, you would measure this x. And it would have a single definite value, namely x. And
Sam, one quick question. Maybe
yes,
you already said this. C number means classical number. Is that right? I keep
yes,
assuming that, but I don't think I ever asked.
Yes. So a C number is kind of short for classical number, which is, so, you know, my statement that classical mechanics is described by C numbers now sounds kind of circular because it's classical numbers, but you can think about it as any number that is an element of the reals, as any number that is a real number, or of the complex numbers. And I'll get to that right now. So I want to, before I get to these Q numbers, I also want to talk about complex numbers. And one of the, well, actually, so one of the things that makes the real numbers is that they have this nice property that any two numbers, A and B, that are elements of the real numbers, well, first of all, you can add them together, and their addition is again an element of the real numbers, and their multiplication is also an element of the real numbers. And moreover, they have the property that the number A times B is always equivalent to the number B times A. So like 2 times 5 is equal to 5 times 2. That's very basic. And this is what you might call the algebra of the real numbers. It's a very simple algebra because, as we say in quantum theory, these numbers commute with one another, which simply means that multiplying A times B is equivalent to multiplying B times A. And in this sense, the real numbers are a very simple number set. There's not many very interesting algebraic properties about the real numbers. And one kind of step up from the real numbers is the so-called complex numbers. So these are the real numbers, then there's complex numbers.
By the way, just if you think this sounds too simple, so far this is very simple. He's basically saying that in classical physics that you use real numbers to describe the state of the system, what its position is, in this case, you know, on a one-dimensional line. I mean, it's that simple. You're not missing anything.
Yes. So part of what typifies the complex numbers is that there is a number, sometimes known as the imaginary number, I, such that the square of I equals -1. And on first sight, this is one of those kind of strange mathematical artifacts, because there is no real number that has as its property that the square of it is equal to -1. So I is not an element of the reals. But it is nonetheless a number. So for example, you can multiply I with elements of the reals. So you can have some kind of multiplication of I times A times I, where A is a real number. You can also add a real number to I. And I is an element of the complex numbers, and so is this sum and multiplication of I. So the complex numbers are denoted with this little symbol, and kind of multiplying a complex number and adding a real number to it is again an element of the complex number plane. Oh. So it's a number in the sense that you have this kind of, you can add things, you can multiply them, and you're still within the same set. You're still, you're not doing anything that is not contained in the complex numbers. And likewise, for any general complex number, you can add these things and multiply them, and it would again be an element of the complex numbers. But they have this nice non-trivial algebraic property that there is an element of the complex numbers I, which if you square it is equal to -1. And I think this is a very nice development in mathematics, because you, in some sense, we can just give algebraic properties to symbols and then treat them as numbers by defining multiplication and addition. And this kind of broadens our conception of what a number could be. And the reason I'm mentioning this is because the Q numbers are an even broader set of things than these complex numbers. And in particular, the Q numbers have, they drop this property that I mentioned before. So there's this commutative property that real numbers have, written here, and Q numbers in general, they do not commute with one another. So now that I've kind of given this, what's hopefully like just a very basic kind of recap of the real numbers, the complex numbers, and of classical physics, and having given this definition of what a descriptor is, I'll now get to the meatier part of this talk, where I talk about Q numbers. So a Q number has the property that when you multiply two Q numbers together, they don't necessarily commute with one another. And perhaps the simplest possible set of Q numbers is a triple called, so I'll write them down. I call them Q1, Q2, and Q3. And I also have this 1, which is just, you can think of as the unit element, or just the number 1 for these purposes here, even though I'll elaborate a bit on that later on. And these numbers have specific properties that make them distinct from the real numbers. So, for example, kind of similar to how there was an imaginary number that whose square was -1, we now introduced certain algebraic properties that these descriptors must adhere to. The first of them is that the square of any of these numbers is equal to 1. And that's simple enough. There are real numbers that adhere to this property. But now, less trivially, we also require that, for example, Q1 times Q2 is equivalent to I times Q3. And cyclical permutations of this are also true. So Q3 times Q1 is equivalent to I times Q2. And Q2 times Q3 is equivalent to I times Q1, where this I is again the imaginary number. So it's the number that has as a property that its square is equal to -1. Interestingly enough, as I just mentioned, these numbers don't commute with one another. So if you were to multiply Q2 by Q1, then this wouldn't simply be equal to I times Q3. It's equivalent to -I times Q3. And Q1 times Q3 is equivalent to -I times Q2. And likewise, Q3 times Q2 is equivalent to -I times Q1. So you see that now we have something that's very unusual. It's unusual in the sense that we have these things which I claim are numbers, but they don't commute with one another. If I multiply Q1 by Q2, then that is not the same as multiplying Q2 by Q1. And yet they're numbers in the sense that we can add them, we can multiply them. In fact, I have defined what multiplication means for these numbers. I can't just multiply them with one another. I can also multiply them with, say, a constant. So I can multiply Q1 times A, where A is just some real number. And this would again be a Q number. I can add them together. So I can add A times Q1 with B times Q2, where A and B, as I said, are real numbers. And this sum is again a Q number. It's a valid Q number. Also, as I just said, there's this number 1, and it can just be, for all the practical purposes in this talk, it is equivalent to just the number 1. So multiplying 1 with anything else is equal to that thing. So 1 times Q1 is equal to Q1 times 1 is equal to Q1. There's nothing special that happens here. The same is true for any other Q number. And this is just to remind you that there are certain numbers which do commute with one another, like this trivial number 1, and also real numbers multiplied by Q numbers. So the real number multiplied by Q1, the real number A multiplied by Q1, that also commutes with Q1 because it's a real number. So these are kind of the basic properties of these Q numbers. They have what we call an algebra, which I've summarized here. So this whole business is what I call the algebra. And we have a notion of adding, of multiplying them together, of multiplying real numbers times these Q numbers, and these are all valid operations. And that is, in that sense, they are real. They're numbers. They're Q numbers, but we have kind of corroborated that they are in fact numbers. And the claim is that all physical systems in reality are described by Q numbers. Not necessarily these Q numbers. This is a specific set of Q numbers. And there's many algebras that Q numbers can have. But all physical systems are described by Q numbers, by Q number descriptors. In other words, the possible physical states that a system can be in are described by a set of Q numbers. And in this case, the set of Q numbers that I've just written down describes a qubit. So these are the algebraic properties of qubits. Now, whenever you measure a qubit, you never really see the Q number. Unlike with C number observables or C number descriptors, you don't ever see a specific single value, or the cases in which you do are special, which I'll get to later on. But something very strange goes on when you measure a Q number. And as I said, you never really measure the Q number specifically, but what you measure is this thing that I'll just call the expectation value. So whenever you measure Q1, there's this corresponding quantity. So there's this corresponding thing that I'm calling the expectation value, and that is the thing that you can observe in a laboratory. And there are certain properties of, or actually, instead of calling it the measurement, I'll just call it what everyone calls it. It's the expectation value. So it's the expectation value. And this is the thing that we can observe in a laboratory experiment. And to kind of give you a brief overview of, first of all, the properties of the expectation value, which again is just the thing that I'm defining here, right? So I have this thing where I draw these brackets on the left and right hand side of Q1, and I say that's the expectation value. But the expectation value also has certain mathematical properties. Specifically, if you have the expectation value of some Q numbers A and B, then this is equivalent per definition to A plus B. And if you multiply some real number small a times capital A, then the expectation value of this is simply small a times the expectation value of capital A, where again, capital A and B are Q numbers. So these are just some mathematical properties of the thing that I'm saying is the expectation value. But by the way, if anyone has questions about any of this, feel completely free to interrupt me, to ask something. I think that's part of the fun of having an audience. And also, if you have a criticism of anything I'm saying, that is also nice. That's appreciated.
So I have a question. Why did you differentiate between a measurement of and the expectation value of? Aren't those the same thing? Is it just one is a bit more clear than the other?
Well, you never really measure the expectation value during a single measurement. So the expectation value is in some sense is a statistical thing, right?
I see.
Like,
right. No, that makes sense,
yeah,
because it could be in spin up and spin down at the same time, but what you actually measure would be one of the two.
Yes.
Okay, that makes sense.
Yeah, so there is always a specific measurement outcome, but from repeated measurements on the same system. So you have like some physical system that you can prepare again and again and again in a certain initial condition, and you perform measurements on that system. Then you can discern what the expectation values are, but the expectation values are in some sense not the things that you measure. They only become apparent from repeated experiments. So
put that in layman's terms, it would only be apparent if you measured it multiple times and sometimes got spin up and sometimes got spin down. That would 50% of the time, then the actual expectation value is 0.5 for both.
Yes, I think this is called tomography, quantum tomography. Charles might be able to corroborate that.
Yes, correctly. Yeah.
Yes.
Tomography.
Where you can repeat an experiment again and again, and from doing the experiment again and again and looking at the like statistical appearance of certain outcomes, you can discern what the state of the physical system must have been in before you measured it. But yeah, so this is just to differentiate between what you expect during any particular measurement outcome, which is unpredictable to some extent, and the expectation value, which is this thing that becomes apparent due to repeated measurements. But anyway, so this is all kind of getting into the specifics of how measurements work, and in a way that's nice because I kind of want to get into that. I want to give some kind of very brief overview of measurement theory. It's not a lot. It's not very. It's not incredibly deep, but it's enough for what we're doing here. And what I'm imagining specifically is what it means to perform a measurement twice. And for this, I will draw a nice little measurement machine. And it has a certain tape. And on the tape are denoted, so the tape contains like different measurement results from past measurements performed on some system that the measuring instrument is measuring. Oh, this is extremely annoying, but sorry for this. So as I was saying, so the measurement device is measuring our Q numbers. So maybe it's measuring Q1, the Q number Q1, and it is noting down what the measurement results are. And you can now imagine what it means to perform a measurement on the same physical system twice. Namely, you perform a measurement in Q1, and it turns out to be to have value A. So the outcome of this measurement was A, with A some real number. So the outcomes of measurements are real numbers. That's important. And maybe the second time that you measure the qubits, or okay, I've kind of set it as a qubit now, but let's just say it's a physical system described by Q1, and you measure this Q1 again, and you have some measurement result B. Then if you multiply together these results A and B, so the result AB, that is equivalent to a measurement of Q1 squared, because it's the square of the measurement results. And we can now kind of learn interesting things about about these kinds of results from the algebra of the Q numbers, Q1, Q2, and Q3. Namely, we can ask, okay, what's the expectation value of Q1 squared? What do we expect to see if we multiply together two measurement results of a measurement on Q1? Well, as it turns out, as we know from the algebra, Q1 squared is equal to 1. So that's that one. So if you zoom in again, this means we're just looking at the expectation value of the unit observable of 1. And it turns out that per definition, this is just equal to 1. In other words, no matter what the specific measurement outcomes are, if you multiply them together, then the expectation value is equal to 1. And there's now a special case where, actually, okay, I mentioned that kind of too early, but let me just draw your attention to another interesting fact before I kind of join things up. Namely, the expectation value Q1 squared isn't always equal to the expectation value of Q1 squared. So, for example, it might be the case that, just we're being completely general here, what if the first measurement result was had expectation value of being like with equal probabilities, you could measure it being a 1 and a -1. Well, if that were the case, then Q1, the expectation value of Q1 would be 0. So the square of the expectation value of Q1 would be 0. And that means that the square of the expectation value would not be equal to the expectation value of the square. Because in certain cases, there's this probabilistic aspect to measurement. You can measure something and you don't know how it's going to turn out. And there's this kind of mixture of results. You have this sense of probabilities. But there's a special case in which, so this is kind of like, this is not always true. This generally, Q1, the expectation value of Q1 squared is not equal to the square of the expectation value. This is always very difficult. It's Q1, the expectation value of Q1 squared is not always equal to the expectation, or to the expectation value of Q1 squared. I think it's the same thing twice.
Almost exactly the same when you say them in English, but they're different.
Yes, I think I'm now messing with myself here, because I think I just said the same thing twice. But anyway, you get what I mean, because it's there on paper, on the whiteboard. And the important case is the case in which the repeated measurement on Q1, so the repeat measurement where you measure the measurement outcome of Q1 twice and then you multiply the results, is just equal to the expectation value of of Q1 twice, right? Because then there's some definiteness. If there is a value for which the expectation value squared is just equal to the repeat measurement, then the expectation value must have been the thing that you measured. In other words, there's a case where if q1 squared is equal to q1 to the square of the expectation value, then it just means that the multiplying these results together is exactly the same as the expectation value. And in that case, the expectation value is the thing that you measured. It must with certainty, you must have measured the expectation value of the qubit. And because of the algebra of the Q numbers, you can now kind of determine when this is the case. You can determine for which values, for which expectation values, you know with certainty what you will measure the qubit to be. And in particular, you'll find that by using the reasoning we just used, by this idea that q1 squared is 1, we see that the values for which we know with certain what the outcome of measurement will be, they must be the cases from which the expectation value squared is equal to 1. In other words, they are the values for which the expectation value of the qubit is 1 or minus 1. And there's now several interesting things about this. First of all, we've just used a very basic notion of measurement, and we've used the algebra of the descriptors. And from that, we've been able to determine when the expectation value must be the thing that we observe with certainty during an experiment. And these two expectation values, 1 and minus 1, are what are known as the eigenvalues of Q1. For all our purposes, what this means is that Q1 is sharp. It's sharp in the sense that it obeys this property, sharp in the sense that if you were to measure it, it has a definite measurement outcome. So this is what I mean with sharp. This is something is sharp if, I'm going to try this one more time. If the expectation value of the square is equal to the square of the expectation value. There we go. I finally said it. And as I said, it's a property of the algebra of these Q numbers. And what we call this is, we say that there is a spectrum of eigenvalues. So there's a set of eigenvalues, 1 and minus 1, and they are the spectrum of Q1. So those are the only numbers, the only expectation values for which, if you perform a measurement on Q1, you'll obtain with certainty that it is in fact that value. It's the only case in which there is a sharp, there's like a definite, where the Q number Q1 has a definite value. It only has a definite value if its expectation value is 1 or minus 1.
So I've got a question about that.
Yes.
So what this really would mean, though, is using my example where you could have a superposition of spin up and spin down, that wouldn't be sharp. But if it was in a definite position of spin up, so that anytime you measured it, it was in a spin up position, that would be a sharp value. Is that correct? Or am I misunderstanding?
Yes. So I've kind of intentionally not talked about any of that.
Okay.
I've kind of left out all of the. I've just started from this idea that, you know, there's these physical systems, and they're described by what I call Q numbers, and you can perform measurements on particular Q numbers. Well, in reality, you perform a measurement on the physical system, and that corresponds to finding out what the Q number is. But you never even really find out what the Q number is. You find out something about the expectation value.
But the word sharp has a fairly layman's understanding. It's you defined it in terms of mathematics.
Yes.
But really, it just means it has a definite value.
Yes. So, for example, okay, let's imagine. You know, we don't have to imagine. We have things that we think are sharp all the time. Like, I'm now looking at a screen, and the screen seems to have a definite value. It's not. There's no. I'm not worried about the screen like being. I'm not worried about the white in my whiteboard being white or black. It's just white. And that is a sense in which the value of the screen is sharp. But though, we're kind of deceived by appearances. We think that things are described by sharp C number observables, where when we perform a measurement on a system, we just measure the C number. So for example, let's say that my computer screen can be either black or white. Then if I were to measure the computer screen, I would see it in one of those states. And that, so that corresponds to maybe a bit. It corresponds to the bits 0 and 1. So there's kind of two states of the screen that I could measure it in. And it will always have one of those values, right? That is not true in quantum theory. Sometimes the thing that you're measuring is not sharp. Sometimes, like if you perform, and what it's saying is sometimes if you perform a repeat measurement of a system, it's not equal to the thing that you expect it to be initially. I feel like I could summarize that better. But there's the sense in which if you, I think I'll leave it with that. I think I'm not going to clarify it more right now. But yeah, so I've gotten to this state where I've been able to discern from certain basic assumptions about what these expectation values are and how measurements work, and from the algebra of these Q numbers, for what values the Q numbers can be sharp. And having done that, I've defined this thing called the expectation value. It's not the expectation, the spectrum of Q1, and that spectrum is a property of the algebra of that qubit. So likewise, the other qubit descriptors, because they have the same algebra, will also have exactly the same eigenvalues. And this just follows from everything we've just said. There's no, like, the square of Q2 is also equal to 1. If you zoom out, you can see that again. The square of Q2 is also equal to 1. So the same reasoning we just applied here for the Q number Q1, it also applies to Q2 and also applies to Q3. So they each have only two values for which they're sharp. Okay, now I wanted to talk a bit about, I wanted to speak a bit about the expectation value and the probabilities of measuring one of these outcomes. And I want to do that by looking at a new observable or a new descriptor, which I will call P1 of, for example, Q1. And this is defined, I think I can write that better. There we go. As, and now I think, as this. Let's just treat this as a new descriptor, as a new observable, and we can ask kind of the same questions that we asked before. For example, what is the algebra of this descriptor? Well, we know that Q1 squared is 1, and we can now ask, okay, what is P1 squared? Well, that is equal to this. Then we notice that Q1 squared is equal to 1. Then we replace certain things and we obtain that this is equivalent to P1. So this is just P1 again. So very nice property of this new operator that I've kind of just defined out of nowhere, and which I'll kind of give more meaning soon, is that its square is equal to itself. okay, that's an algebraic property. Now we know that from the algebra of a descriptor, you can determine the sets for which P1 is sharp. So what are the numbers for which P1 is sharp? What are the expectation values for which P1 is sharp? Well, P1 is sharp if P1 Q1 squared is equal to P1 Q1 squared. We have this algebraic property, we plug it in, and we rewrite the square of P1 just as P1 and now we notice that the values for which the expectation value of P1 is sharp must be those values for which the square of the expectation value is equal to the expectation value. Now, there's only two numbers for which this is true, namely 0 and 1. So the spectrum of P1 of Q1 is 0 and 1. And what it turns out is that this descriptor is the probability that you will measure the value 1 of Q1, which is why there's this little subscript 1 for P. In other words, this expectation value is the expectation value, is the probability that you will measure Q1, so the thing in the argument, to have value 1, the thing in the subscript. And if, for example, P1 is sharp with value 1, well, then it follows from this that Q1 is sharp with value 1. And in fact, you can kind of prove this mathematically by just using the definition of P1. So if you take the expectation value of P1, well, we know that this is the expectation value of a half, 1 plus Q1. Now we know from my definition of the expectation value that we can, that this scalar multiplier in front of this little term, well, we can take that out of the expectation value. And also we can rewrite this as just the expectation value of the sum of Q of 1 and Q1. And we know that the expectation value of the unit observable of 1 is just 1. And now in the case in which P1 has expectation value 1, it follows that, so the left-hand side must be equal to 1 and the right-hand side is equal to this identity. And with a bit of mathematics, it then follows that Q1 is sharp with 1. So this is just some simple rewriting. And there's only one, and as soon as Q1 has the expectation value 1, you know it's sharp, kind of per definition. Likewise, if P1 has expectation value 0, you can show that the value of Q1 must be -1, which again makes sense, because if you have an expectation value of, if the probability, which I'm claiming these expectation values, this expectation value of P1 is equal to the probability of measuring 1, if that is 0, if you have probability 0 of measuring Q1 to have value 1, well, then it must have the only other sharp value, and that is -1. So if the probability would be, or if the expectation value of P1 would be 0, then Q1 would have value -1. And the so this projector is like a probability. It has a value between 0 and 1, and these values correspond to how likely you are to measure Q1 to have value 1. Likewise, there must be another operator. So we've defined P1 Well, we can also define a thing p minus 1 of q1, which per definition is 1 over 2 times 1 minus q1. And like p1, p minus 1 has the property that its square is also equal to q1. And so it also has two sharp values, 0 and 1. And these and these again correspond to probabilities, but in this case they correspond to the probabilities that you measure the qubit to have value -1. In other words, I'm giving you these two operators and I'm telling you, kind of inserting into the theory. I haven't really argued for why this has to be the case, but I'm inserting into the theory that the expectation values of these descriptors, P1 and P minus 1, are the expectation values for measuring respectively the eigenvalues 1 and -1 of the descriptor Q1. Now, again, I have just inserted this. This is an assumption that I've put in. It's an assumption that with kind of advanced arguments, you can prove from simple assumptions about quantum theory, but I'm not going to get into that here, unfortunately. This is known as kind of the Deutsch-Wallace game theoretic argument for probability. That's very advanced stuff. Maybe, I'll discuss that in the future, but that's not for here. All you have to know here is that I'm assigning kind of as part of the physical theory, I'm saying the expectation values of these descriptors are equal to the probabilities of these of measuring a 1 and a -1. And as a kind of final thing to this lecture, there's a property that these descriptors should now adhere to, which is that if you add the probability that you'll measure a 1, which I'm claiming is this expectation value, with the probability that you measure a -1, then the probability that you measure any of the possible values that the qubit can have, that should be 1, right? You should, the probability of measuring anything at all is just 1. With certainty, you'll measure the qubit having some value. And this is now a constraint that the system should adhere to. Does it adhere to it? It's an interesting question. And you can prove that it does. You can prove that this requirement is satisfied. And the way to do this is by first noting that if we look at P1 Q1 plus P minus 1 Q1, well, this is per definition equivalent to a half 1 plus Q1 plus a half 1 minus Q1. And when we add these two together, we see that we can cross out these terms because they're just equivalent up to a minus sign. So this thing on the right-hand side is just a half plus a half, which is equal to 1. In other words, the expectation value of P1 plus P minus 1 must be equal to 1 because of their algebra. So from the algebra and from the definition of these operators, it follows that their sum is equal to 1. So this kind of corroborates that they represent expectation value, that they represent probabilities. And yeah, so with that, I kind of want to round it off. We've covered, I think, as much as I wanted to cover in this informal lecture. And so to recap, what we've seen is that you can consider a world in which physical systems are described by these Q numbers, these things with non-trivial algebraic properties, and from very simple assumptions about like the theory of measurement on these descriptors, you can discern very interesting facts about them. And you can see, for example, that they're not always sharp, that you won't always with certainty measure a particular measurement outcome. You can see that the values for which these descriptors do have are sharp are discrete. So in the case of Q1, Q2, and Q3, they're only sharp if they have value 1 and -1. And you can discern a whole lot of very non-trivial properties from their algebra. And yeah, with that, I want to conclude the talk for the moment, and open up the floor to questions if there are any.
Yes, thank you, Sam. Does anybody have questions about this? I just wanted to make a quick comment myself that I had studied quantum computation before I started talking with Sam, and they actually don't teach it to you this way. So I was actually really surprised. This explains why we treat quantum physics as probabilities. I had never seen that before. I found that really fascinating, actually.
Yeah, there's a lot that goes into this assumption that you don't really measure any one of the Q numbers, but you measure their expectation values.
Yeah.
That is, yeah, there's a lot of interesting stuff that happens there. And yeah, so far, this is like the most concise way in which I've been able to summarize simply how, yeah, you can treat Q numbers as describing physical systems.
Does anybody else have questions? I mean, I get it that this is even as much as he has simplified this is still obviously a tough subject. So, but does anybody have questions they would like to ask, either about this or about anything related to this, his paper, or just some questions in general about quantum physics that you've been wondering? And you've got an expert here that has worked with David Deutsch on many worlds.
Yeah, so I maybe have a question. So who came up with this theory, and what in what the theory responded to, what in fact, to what need?
What
maybe
problem?
a little bit what problem or what need with like other approaches. So a little bit like how it originated and in response to what, or to indeed, yes, what kind of problem with classical between brackets, classical approaches to quantum mechanics.
Yeah, well, so one of the motivations for quantum theory comes from the fact that atoms have a spectrum, so a light spectrum. So in other words, whenever, let me see, wait to start with this. When an atom has an electron that decays to, like, it's in some orbit around the atom nucleus and decays to a lower orbit, it only does so in jumps. There's only specific energy values that the electron that's orbiting the atom can assume. And this was very puzzling for a long time. And it's related to things like the photoelectric effect, which Einstein worked on. And one way in which this spectrum of energy values was kind of used for a deeper understanding of physics was by Heisenberg. So Heisenberg had this idea that there's these rules for multiplying two classical numbers with by one another, and there's rules, for example, for how you get the square of a number, which are just like very simple rules. It's just you square the number, and Heisenberg had in mind, like, okay, if you have this is maybe, I'm not sure how to summarize this in a way that's simple, but he had in mind that there's a Fourier series in which you can express, say, the position of an electron, and it's this thing with coefficients and like some complex spaces. And he said, well, these complex spaces, they must be equal to the energies. And so now if you, this I think this is slightly too complicated, but he had that notion of, we have a Fourier series, and I put in this fact, he put in the fact that the energy values of the electrons were quantized. And from that, he found that that multiplying, for example, the position is equal to matrix multiplication. So the square of the position was like the square of a matrix. And that was the only way in which he could make sense of the fact that the energy values of an electron, say, were quantized. And that's where this way of representing physical systems started. It started with Heisenberg, and started with him trying to make sense of the spectrum of the electrons and of atoms. So I think I just said some things there which might not have made sense, and I think I also said some things which hopefully did make sense. And the really short answer is just, it was Heisenberg. He started with this because of the atomic theory.
Yeah, I see. But then also with the Schrödinger picture, you can calculate those energy levels as well.
Yes.
So where do both diverge, and where does the one add more than the other?
So so what I've just described is what's sometimes known as the Heisenberg theory of quantum mechanics. In a way, so the Heisenberg picture and the Schrödinger picture of quantum mechanics are distinguished by which things evolve in time. And I have not talked about evolution. I have not talked about anything evolving. So in some sense, there's no distinction in my case between the Heisenberg and the Schrödinger picture. But when you talk about evolution of a physical system, then you can either evolve these Q numbers, you can evolve Q1, Q2, and Q3, or you can evolve whatever it is that gives you these expectation values. And in a sense, the Schrödinger picture is doing something to these expectation values, and this Heisenberg picture is just evolving the Q numbers. And evolving the Q numbers is nicely symmetric with how we treat systems in classical physics. Because in classical physics, we're used to there being a descriptor, it's time dependent, and that time dependent descriptor gives you the state of the system at any particular time. Like if you have the position, then you know that the position at time t is just this descriptor x of t. And in a way, the Heisenberg picture is like that. It's like saying, I can use the whiteboard for this. It's like you're saying, we have these Q numbers, Q1, Q2, and Q3, and they are also functions of time. Whereas in the Schrödinger picture, what you do is you in some sense, you say, okay, well, it's, you have this thing, the expectation value, which I have not really described here. It doesn't have, it's not clear what this expectation value is, how you obtain it. I'm just saying it is there, and it has certain mathematical properties that I've defined. But let's just say there's an empty expectation value. What if you just evolve that forward in time and you keep these Q numbers fixed? It turns out there's a symmetry between that and between evolving the Q numbers forward. In other words, if you evolve this expectation value forward in time, that turns out to be the same as evolving the Q numbers forward in time. Whereby, when I say evolving the expectation value forward, I'm saying the function that maps the Q numbers onto the real numbers somehow changes with time. And in the latter case, I'm saying these Q numbers actually just become different. But I've not talked about evolution here. In my picture, everything is stationary. There's no sense in which anything evolves. But okay, that's the difference between the two pictures in terms of mathematics. The Heisenberg picture is nice because it's the only picture in quantum theory in which there is, well, it's the only description of quantum theory that's local. It's the only description in which if you do something to, say, system 1, then which is spatially separated from another system 2, then your operation on system 1 does not in any way affect what's happening to system S2, to system 2. It's, in other words, as Einstein put it, the real factual situation of system 2 remains unchanged if you perform an operation on system 1. And the Heisenberg picture is local in this sense. It's local in Einstein's sense. And yeah, I think that's a good property for a theory to have, for a description to have.
I have a question related to your previous answer. It seems like quantum physics is, I don't want to say unique, but rare in that the theory was derived without an explanation, or at least without a full explanation. It almost seems strange to me that would be the case. And maybe that's not as strange as I think. Obviously, the explanation actually ties into this whole idea of many worlds, but they didn't know anything about that at the time. And the way you just described it, it was more like he was trying to solve a problem and he noticed that mathematically, at least, that you could put it in a matrix and square it. I mean, there's almost this instrumentalist approach to how quantum physics came about. Can you comment on that? Am I getting a wrong picture there, or is that really kind of the case?
Yeah, I don't think it actually came about in an instrumentalist way. I think that quantum theory, there were all kinds of problems that led to quantum theory, and there's maybe too many to cover in a single answer. But one of my favorite ones is that there's no explanation, completely separate from anything I've covered here, but there's no explanation for magnetism in classical physics. This was actually a problem that Bohr worked on during, I think, his thesis. If you try to deduce the magnetization of some material that's like a refrigerator magnet, right? This thing that has like some intrinsic magnetism. In classical physics, it turns out that the magnetization of any macroscopic material, like a refrigerator magnet, must always be 0. In other words, according to classical physics, things like refrigerator magnets don't exist. That's a purely theoretical result that was proven by him and von Leeuwen. And that was one reason for, well, that was one problem with classical physics that motivated there being something like quantum theory. And in fact, there's a whole line of research into these magnetic materials that exist now. And all of that, in fact, there's a field called Condensed Metaphysics, which is about the properties of macroscopic materials like metals, like chairs and tables in some sense, and magnets. And that theory, that field only uses quantum theory. It's completely dominated by quantum theory. There's no real classical physics that's used in that field. And I think when we think about, the history of quantum theory is often described as, oh, there was a measurement that didn't make sense, and then people just postulated the wave function. That's not really the case. There were many things that led to the discovery of quantum theory. One of them was atomic theory, and even in atomic theory, there were many things that were not instrumentalist problems, like say the fact that atoms couldn't be stable. That fact alone, I don't think that was that was not a experimental problem. It was a problem in the theory of atoms. It's like, okay, if you have this, this thing that is rotating around a nucleus, if you have this electron rotating around the atomic nucleus, then that thing if it's classical, must emit energy, because anything that is rotating in classical physics and has some charge must produce light. And so this thing that's rotating must slowly collapse to the center of the atom. And that's a theoretical problem. That's a problem of how, it's a problem in the theory of atoms, which again motivated quantum theory. And lots of this simply wasn't instrumentalist. Lots of it was problems with classical theory, purely theoretical problems. And those, as well as certain experimental results about, say, the heat capacity of materials, and also the fact that there was no such thing as black box radiation, although even black box radiation is in some sense a theoretical problem. Those led to the discovery of quantum physics. And then, you know, with that was a radically new theory, and and as we now know, with many years of research behind us, there's a new kind of information in quantum physics, and the early quantum theorists just didn't know about any of that, and they had a hard time making sense of it. I think they also they had bad philosophy, but we should cut them some slack, because they did solve lots of very important theoretical problems.
Dang, almost proved instrumentalism true, foiled again.
Nice.
All right. Anyone else have questions?
I have a question.
Cool.
Yeah, Sam, do you know about quaternions?
Yeah, I should have maybe just called them quaternions from the start, but yes. So these are quaternions.
Pretty much, yeah, exactly.
Yes.
Okay.
Yeah, they're quite fascinating.
Q numbers are, what are they? Quaternions?
Well, so the sense in which I use the word Q number just means any number that doesn't commute. So if you have two numbers, A and B, and the product of A and B is not commutative, then that's what I call a Q number.
Right.
And I think that's how people use the term generally. It's not very well used, very used anymore. I think it used to be like, I mean, it's a weird sentence. It used to be used more. But like if you read Dirac's quantum mechanics book, then he will use the term Q numbers, as well as I think people like Wheeler, maybe Feynman. I'm not sure about Feynman. Anyway, but so it's a very broad class of numbers. Quaternions specifically are the numbers that have this algebraic property. So it's any linear combination of these things. As I understand it, it's any linear combination of these things, where a linear combination is just so this here is a linear combination. It's either a sum of two things, or a product of two things, or a product and the sum of two things. And the complete set of numbers that you can make by multiplying and adding these four basic elements is called the quaternions. And I've kind of swept a lot on the carpet, I think.
Yeah.
Including the name quaternions. Yes.
No.
Well, I mean, this is
like
also thing I should have mentioned. Like that, I should have mentioned that when I was talking about the measurement, for example, I didn't really describe what kind of thing we were measuring. I was just saying we're measuring a system that is described by these Q numbers. But I should have said in this measurement example, just for completeness, this is a qubit. So these Q numbers that I've written down here are the descriptors of a qubit. And as Charles said, the descriptors of a qubit turn out to be quaternions. They are kind of, per definition, a qubit has descriptors that are quaternions.
Okay.
Yeah. To be, I think, technically correct, I think there's a little mapping that needs to be done before we retrieve the algebra of quaternions, which is
that's right. Yeah.
you have a minus I to add pretty much everywhere except on the unity.
Yes.
And I think in this case, it satisfies ij equals k, and but yeah, sorry, your redefined Q1 times your redefined Q2 would be your redefined Q3.
Yes.
Because I think that is the algebra that they need to satisfy. But it's basically the quaternions. That was one of my questions, but then the other one, I think you touched a point. But I'm glad you say that Dirac's book, in fact, speak about Q numbers, because nowadays we don't hear it more. And I was curious to basically straightforwardly ask you, why referring to Q numbers and not an algebra of operators, which is more common in the field, I think.
Yeah, well, I like the term Q numbers. I like this idea that we have classical systems which are described by C numbers, which are sharp and have certain trivial algebraic properties like they commute. And then we have these things called Q numbers, and they are the descriptors of quantum systems. And they are things that don't commute with one another, and they're more complicated mathematically in some sense. And you can then formulate in a nice conjecture what I think of as like the fundamental principle of quantum theory, which is that all descriptors of physical systems are Q numbers fundamentally. And that is like the word Q number is doing a lot of work there, because I have to say, like, what is a Q number and what's a descriptor? And yet I think that is an incredibly important part of quantum theory, that all the descriptors of physical systems are in fact Q numbers. So,
and does that mean never C numbers?
Yes,
Or,
I think it should mean never C numbers. Yes.
Okay, yeah.
Yes, so it's in the sense of, if you think of C numbers as the things that commute with one another, and then you think of Q numbers as the things that don't necessarily commute with one another, then they are non-overlapping. But it's all a bit fuzzy, admittedly.
Yeah. Okay.
But I'm a physicist.
Because for instance, I don't know, but space-like separated observables would commute.
Yes, true.
But then they're not C numbers just by the mere fact that they commute.
Yes.
Are they? Yeah.
Yeah, they're not. So you
No.
Yeah, they don't commute individually, and they do commute with one another. But also, as you know, I'm skeptical of the fact that they commute when they're space-like separated. So
yeah, that's true. Okay.
So for those of you who don't know, there's this principle of quantum physics, which says that if you have, so I've been talking about a single quantum system with these 3 Q numbers, and when you go to more quantum systems, when you say you have 2 qubits, right? So you have 2 sets of these 3 descriptors, then there's an assumption about the commutation relation. I see I stopped sharing. Yeah, there we go. There's an assumption about the commutation relation between the descriptors of one qubit and the descriptors of another qubit. And what we say is, well, individually they each adhere they adhere to this algebra that I just showed during the talk, which is known as the Pauli algebra. But when you look at the descriptors of the 2 qubits and their products, then they just commute with one another. They multiplying a thing on this side with a thing on this side is equal to first multiplying a thing on this side with a thing on that side. And that's an assumption of quantum physics. Is whenever you have multiple systems, you just multiply. You just assume that the usual kind of trivial multiplicative identities hold, so that everything commutes at space-like separation, but not if you look at the qubits individually. And I hope that was somewhat clear. That's a much higher level concept, but yeah. Anyway, yeah. Thanks very much for having me, and thanks for all the questions. And it was a pleasure. It was great.
Thank you, everybody.